match, and if you watch soccer match in TV, you will see that kind of small numbers, typically on the left hand side, the bottom part. And so as I was looking, watching this kind of soccer matches, especially those are telecast from Europe in particular. So I was amazed by looking at these numbers, which is the possession, right? Possession statistics they call it, ball possession statistics. So I started inquiring how these numbers are generated, and then eventually I got interested to these origin of these numbers, and then we had a project and we worked with this. Two students got PhD, but by academically posing different problems involving these numbers. So the first problem is regarding this. The second problem was a funded project. Earlier one also a funded project. This was the funded project from the TCS. As you can see, it's primarily a bunch of products on the racks of shelves in supermarket. And the problem is very simple. You take a picture of these images of these racks, and you identify the products of the racks. Right? That's the simple one. Or the another layer of the problem is that all these large shops, which I didn't know earlier, that they have a plan of displaying these products, so that they can psychologically influence the customer, and they call that as a planogram. So the problem, in other hand, is a planogram compliance. You take a picture, recognize these items, and match with the plan. That's the planogram compliance problem. The third problem is a very standard problem. We had this earlier about identifying human actions and emotions. This in particular is a data set, a benchmark data sets freely available, where the challenge is to identify actions like pointing, digging, walking, running, etc. But as you can see here, the camera is far away from the objects. Right? In fact, these are called the tower data set, because the camera is on the tower and they're looking at persons performing these actions at the ground, right? And these are data sets from UT Austin. So there is a tower in the UT Austin, and from that tower, the tower data sets. Okay, so let's start with the first problem: ball possession statistics in soccer. Again, these numbers has to be calculated. Only the first row of this small table. The others are more challenging, and I hope to work someday with that. Or maybe some of you can pick up that problem. For example, how many attempts have been made in the match? Automatically, you can look at the video and can estimate that. Okay, this is an important statistics, and the strength of statistics is shown here. If you track soccer, the FIFA World Cup final match in 2018, France has 39% and Croatia has 61% possession of the ball. Do you know who won the match? France won the match. So statistics is what? Completely misleading. So it means nothing basically. I mean, even if you have a very lower percentage of ball possession, the ball was very few minutes with the team, but still they could overpower the other. Gaurav is here. Well, okay. So that's an interesting point. Of course, there are good publications in the area of ball possessions, and they primarily relate the ball possession statistics with respect to the control of the ball and control of the game. It's considered as to be one of the quality key metrics for a game, for a soccer game in particular. And so there are other parameters like team chemistry, attacking capability. All these may be influenced by these ball position statistics. But at the end of the day, as I shown, that maybe it doesn't mean anything. But for a good strategist, maybe this is one starting point. overpower the other team in the game. Okay, so what is the existing method? The existing methods, when I inquired, we found out that it's very simple. There is something like a chase clock uh, available with somebody who is actually watching the soccer match. And chase clock means there are three buttons. If the ball is with the team A, then you press the one button. If the ball is with the other team, presses the other button. If the ball is in dead ball condition, then you press the third button. And after 10 or 15 minutes, you see for how many minutes is with team A or how many minutes with team B. That's how you throw away these statistics or garbage. But that's how it's being done. There is, in literature, there is yet another method to calculate these ball position statistics, and that's what it is like this in terms of a valid pass. So in terms of a valid pass, so you can see that position statistics are calculated as number of valid passes of a team divided by total number of valid passes. And what is the definition of valid pass? That is very important. That a player kicks a ball goes out, and it ends into the other player's foot. Yeah. Of the same team. That's very important point. Same team, and that's why it's a valid pass. If it goes to the other team, then it's an invalid pass. And not only that, if the pass actually goes from the same player to same player, in the sense that the player is running along with the ball, then it's not considered to be a valid pass. So we have actually followed these methods, and the work that I'm going to describe is basically by solving this, calculating the number of valid passes, and then calculating the position statistics. So overall, the scheme is like this. There will be soccer video. Player and ball will be detected. It is a difficult problem. It never works better than 70% or so. But it's difficult. In a game, finding out ball and player all the time would be a difficult problem. And once these are identified, then the values pass will be identified, and finally the statistics will be calculated. So our whatever presentation I'm going to do it right now is only in this area. So I'm assuming that this player and ball are detected by some means. So we're going to see that pass detection problem or valid pass detection problem, and we pose that problem as a flow network. Flowing something in a bit. So essentially the pipeline looks like this: frame sequence, detect ball and players, and then pose this problem as a network flow problem. There are video, I assume that we understand the videos are series of frames, right? Typically 25 frames per second or 30 frames per second. So maybe you don't have to take all the consecutive frames. You take the first frame, maybe the 10th frame, the 20th frame, and analyze this network between the first frame and the 10th frame, or 10th frame and 20th frame, and that's how we detect the valid pass. So if we look at the anatomy of the pass more clearly, there are three phases. There will be a split condition in the sense the ball and the player will get split up, and then the ball will have a free run, and then the ball will end, so there will be a march. So our objective would be to detect a sequence of split, move, march. So the network will actually recognize that. And maybe you can come up with much brighter methods. But the way we looked at it is kind of a tracking problem. So it's a tracking of these three events, a sequence of events. Okay. So if you have to model it in a network, the first point, the initial point that you can think of is that here is a frame, let's call it frame L, previous frame. Here is the right frame, maybe 10th frame or 20th frame. Within a second, ball hardly moves, so you can consider first frame and the 30th frame also. So that's the left frame, that's the right frame. And what we are interested to know, that basically the correspondence between these these boxes. These boxes are identified players and identified ball. So if you could find out the correspondence that this blue rectangle goes to this blue rectangle, this red goes to this red, then you can actually track these positions, and therefore you should be able to estimate the movement of the ball and therefore track the value passes. Okay. So you can also say this problem is finding the correspondence of these frames. At some point of time, we worked with the biological states, blood flow in in live human organ, but mainly the test was done on the animals, called the small animal imaging. So on the small animal, it's a very painful process for the animal. So actually, small animals are fixed into a jig, right? So they're fixed, for example, frog or guinea pigs, and then just to give an analogy of another application. So and then take an M&T paper and rub part of the skin. The animal is lying, and you take a picture of that blood flow. And in the blood flow, you track the blood cells. Okay? It's the same problem like that. So it's a flow of those cells, and under different kind of germs or diseases, how the blood flow changes, or how the blood flow or the shape of the cell changes. That's what is a problem of interest in the medical images. So we got certain idea from there as well. So LO1, L2 are those boxes here on the left hand frame, R01, R2, R3 on the right hand side, where we could identify the balls separately. The question is, what is the best path in this network? That's what we would determine. All possible connections are made, and each of these each of these edge will have a cost associated with that. And naturally, as you can understand, the cost can come from certain properties of the box along with the certain properties of that box, and then you can actually correlate between those numbers. But what happens in reality is, when you are looking at a particular frame and the same frame after maybe 1 second or so, then it might happen that certain player just appears there, and maybe certain player goes out of the frame. Right? So in addition to that basic vanilla network, we have added now an appearance node and a disappearance node. This will allow me to introduce a new player or some player going up. So now these detected boxes plus the appearance and the disappearance. Once again, to give a valid, to copy the definition of a valid pass, what you can do is we can take that idea of the rule that there will be a split, move, and march. So we need to have a split node where the ball and the player will get separated, and then maybe after some time they get marched. So there has to be a march node. So in addition to the validator node, then therefore we have the appearance node, disappearance node, we have a split node and a march node. I mean, you could complicate this scenario even further. For example, partially visible. It might also happen that, in fact, those are the reviewer comments we got from the journal in the first cycle, where we said that we didn't address all those questions. It could as well happen like the game was on, and then it was a dead ball situation. The game was not contributed there. So those are more complicated scenarios which we have not taken care of here. Right? And so this we consider to be our final result. And these are those costs. We took those color similarity, the distance in the sense that in a frame, the player was in a particular position, the L frame. In the right frame, the player should be also very close to that position of the initial L frame. So that distance with respect to the origin of the frame should be smaller. So this is also another cost. Angular displacement. So if the player is moving in a particular direction, it has got an angle with respect to the, let's say, the x-axis, and that angle should be maintained for considering the correspondence in the next frame. So these are some of the associated costs. We have also taken the split and march cost, appearance and disappearance cost, and considering all the cost, we solve this network flow problem as a LPP problem to be solved. Now, in the LPP problem, generally you have an incidence matrix, right? And then there is a decision variable x. That decision variable x you need to solve with respect to the flow requirement. Flow means, so if you consider this to be a network, so the network will have a source node and a sink node. From the source node, certain amount of flow getting into the system, right? And then all of them sink to the other end. So here is the source node. This is the total flow going out of the source node. Cardinality of the R. So number of nodes on the right hand side, that's the R, plus the boxes at the left, that is the total flow. So this flow starts from the source node, and all of them again sink there at T minus. Within this source and sink node, you basically get the total flow requirement, and you solve for x. So it's a standard linear algebra problem. The only twist here is it's not just a simple incidence matrix, but it's a coupled edge incidence matrix. Coupled edge in the sense that more than one edges exist from one particular point. So if you actually look horizontally, these are the nodes. So T plus is my source node, L1, L2 on the left hand side, appearance node. These are right hand side players and ball. This is the disappearance node. This is the sink node. And this plus 1, minus 1, plus 1, minus 1 are essentially the connections between node L1 to node I, or node A to node B. This is how the connections are there, but more than one connections are allowed in this incidence matrix. So therefore, these are called coupled edge incidence matrix. By the way, there are very good tutorials available on solving this kind of network problem. And the objective is to solve the X decision variable. So, solution of this decision variable means essentially we will find out the valid paths or the correspondence. So, the point L1 here matches with R3, something like this. If you could solve this, then we know that this is part of a, remember that split, move, and march rule. So that rule can be derived from the solution variable x, right? And that's how we count the number of value passes. So that's how I got the coupled edges, more than one edges to one particular. So that's the solution, which actually essentially gives the correspondence between the two frames, and from the correspondences we can calculate the number of value passes. Okay, so with these implementations, so these are some of the leveling of the. So from the decision variable, we are trying to level that: is it in the march condition, is it in the split condition, or it is in the move condition? That leveling is being done here. Okay, so I think I have a video here, but that's just a toy example of or MATLAB implementations. So in a slow movement, when the ball and player detections are quite perfect, then the program works pretty good actually. So I think it's more of a challenge is to identify these ball and player at the real time, synchronized with the speed of network flow solution problem. Okay. So these are some of the results. We run it on the 8 broadcast video. Fortunately now, Google is everywhere. So Google also has a Google football platform, Google soccer platform, I think. So you can actually collect a 90 minutes video completely with the coordinate data for each and every match. So that gives you a very good, powerful benchmark to compare your work. So these are all synthetic games. So it's synthetically players are actually playing for 90 minutes, and the game is completely recorded with precise coordinates of ball and the players. So those data are now available. So we have run on 290 minutes video on that as well. And there is an interesting twist to the problem also. So the Google camera, Google video soccer data takes the picture from the top of the match, top of the game. So you get a correct coordinates. So in this case, you can understand that the camera is on a side view. So therefore, whatever you are looking at, you are not going to get a perfect coordinates while validating the system. Right? There will be certain amount of distortions. But if you have some positions, some camera, but in live video broadcast in the soccer matches, the cameras are always on the side, not on the top. Very rarely on the top, maybe one camera not covering the entire field. So validation is a challenge in some sense. In fact, one of the reviewer pointed out that in some point of time. Okay, shortcomings. The shortcomings is that in our network, two members from the previous frame can get merged. So our idea of merge node and split node is like player and the ball can merge, two players can merge. Similarly, split, two players can split, one is tackling the other, and player and ball can split. So this is kind of a free form situation where there is no restriction of merging and splitting. That has created a problem in certain results. And so academically that is an advantage. You write another paper. So we just converted that challenge to a new problem. So by the way, CDPR has a workshop on sports analytics. Right? So our first work was on published there also, and then one of the problem was that these results where there is no restriction on split and merge. So that was a situation. L01, L2, L3 may be on the left hand side, R1, R2 on the right hand side. Here there is no restriction. Anyone can merge, anyone can split. But in reality, what happens is maybe L3 can only be split. Why? Because L3 has a previous history of merge. If there is a merge, only then they are allowed to be split. So that restriction is being put in the earlier version. So in the new version, in the new modifications of the architecture, we actually incorporated this change, restrictive allowance of the merging and splitting. So that means that in a match, as you see the frame, you form a group, and you allow the group to go for merging or splitting. So this any box from here and here can never merge. So the idea of group is introduced in this modification. This brings in a new challenge also. Any guess what could be possible challenges? So identification of group itself is a problem because how do you define the group? The way we define the group is simply by taking the distances. So you just find out the distances between the players. So these are 5 boxes and versus the other 5 boxes. Find out the distance, put a threshold on the distance, and that's how you say this belongs to one group. This group of boxes in one group. Right? This is one group. This is one group. This is a singleton group. So this is how we define the boxes, or rather the group, and allow only these to merge and split. But the challenge is somewhere like this. So in a video, in a game broadcast video, what we have seen is that if this is a group, at a certain point of time, the players may switch their positions. So one player was left with the other player, then after some time they become on the right. So the architecture within the group or the positions of the boxes within the group may change. So therefore your cost should also take care of that change of positions. That understand? Okay. So that's what we looked at it. We now earlier we were looking at the similarity of each boxes. Now we are looking at the similarity of the group. So these are those left-hand side nodes, L1, L2, L3, and there is certain amount of relationship between them, and we could have some features H1, H2, H3 associated with those boxes. These features can come from the color, shape, and other properties. Now the question is, this is a group at say time t. Then at time t plus delta t, these L1, L2, L3 may have a different kind of configuration because all of these are dynamic, they are changing in their positions. So let's find out the characteristics of that group after t plus delta t, and then find out the similarity between these two groups. If they are similar, then we are saying that okay, this is the same group. Even though players have changed their position, they are the same group. And we have seen that there are similar works in the field of graph convolution networks. There are a couple of good references on that. And you can actually calculate the feature matrix of a group, or rather it's a subgroup. You can say part of these players, this is a small group of players, they can dynamically change their positions, but even if they change their positions, their feature matrix values can be calculated and their correlation score can be measured such that you identify that the players change their position but the group remains in there. And this can be shown mathematically that this measure, whatever is calculated here, is rotation invariant and translation invariant. So when L1, L2, L3 changes its position, there will be rotation and translation issues. This chat is. Okay, so this measures, if you look at it, it's the degree matrix. Degree matrix of this is the adjacency matrix. So K defines the adjacency. These are the examples. These are the connections. This is defined with K. This is the degree matrix of K, and H is the feature matrix. That gives the some property CL for it. Okay. So this is how. So effect of changing position. That's what we're discussing. So if L1, L2, L3 change position as L3, L2, L1, we can calculate CR, CL and CR, and then find out the relationship between CL and CR to declare whether this group and this group are same or not. And these, by the way, are ordered. These nodes H1, H2, H3, L1, L2, L3 are ordered based on the sorted values of the H1, H2, H3. But this is an interesting area of work when a relationship changes dynamically with respect to time, how to measure the similarity in a video tracking problem. Okay, so these are the related costs once again for the group. So now it's not individual nodes. The individual nodes now represents a group. And these are some of the results. Just skip that very quickly. These are on different data sets. We did some application studies. These are the results on the precision recall curve. The last point that I would like to mention in this particular application is that we have extended this work and published on the applications using the reinforcement learning. But so in that case, this is the total pipeline of calculating the ball position statistics. These are frames, detect ball and players last time, and then use this network. Three of these modules we replace with understanding a state sequence. So I'll explain what state sequence is and detect a valid pass from the state sequence. So when we use the reinforcement learning, all these blocks are replaced by this. Now the advantage of this approach is that there is no need to identify these ball and players individually, because we have seen from an image processing point of view, it's a real challenge to identify these nodes accurately for in a longer period of time in particular, especially in a broadcast video where there is no restriction, because it's sometimes looking at the spectators going back to the field, going from a long shot to mid shot, so there are many restrictions. Okay, so how do we pose it that way? I mean, why we are discussing that in a flow network problem? So a valid pass we have defined as a kind of a state sequence. So we can consider, let's say we are analyzing team A. So the ball is with team A, and after some time the ball is with no one. Let's call it a state NP, and then ball again comes back to the marking condition. So TA. So if there is a sequence of like TA, NP, TA, etc., then identification of the state sequence actually gives the identification of valid passes. So we can actually draw a state transition diagram for this particular. So instead of identifying those boxes, ball and player, through image processing technique, it's a training process. It's a machine learning process where the state sequences, round truths are available, and this is taught to the system. And you can think of this as a reinforcement learning problem, where I don't have that particular slide here, where we are saying that you are taking actions A1, A2, A3, and based on these actions, these states are being changed. So if you know, if you remember the reinforcement learning definition, that some actions has to be taken. Based on the actions, a reward has to be calculated. So in this case, the reward is basically the state positions, TA, TB, and actions are A1, A2, A3, which will A1 will be responsible for TA, A3 is responsible for TB, the ball is TB, and A2 is responsible for no pass situation, the ideal ball situation. Right. So this is yet another graphical model that exploited for reinforcement learning. Okay, so this is the problem 1 that we discussed. The second problem that I mentioned is a funded project where we are identifying these boxes, and as you can see, the problem is very difficult. It's in a real time store associates. They have handheld devices. There is no standardization. So the first restriction we wanted to put that all images has to be taken in a particular fashion with a specific camera, with specific distance, and the company immediately said, then you don't have to take the product. Right? So no restrictions. Free hand. We had actually a couple of patents, 4 or 5 patents on this method, but I think only 2 trial runs that happened, and both of them are failing. Could not actually work significantly. They're very interesting. One trial run of TCS was in Hong Kong, and the height of the stored associates are not significant. Gap between the 2 racks are small, so all pictures they are taking are skewed, and it is getting into our system and it's not giving the desired. I think the Australian trial was far better. Australian trial was significantly better than that. But in a highly packed scenario like this, detecting multiple stacks, you have to identify how many stacks are there, and all these are very difficult. Even if you can identify that this is OEO, you cannot identify exactly how many stacks of OEO. But they want that specific difference. Otherwise, it's not working. Even if you just say OEO, that's not enough for you. So overall, the problem is very challenging. So those who are not familiar with the problem, it's the same age-old computer vision problem. These templates are already given to you. So these are marketing images. These are very perfectly taken, right illumination condition, right background. These are given. This is from the actual store. So find out those items here. Even this is not, they can only say this is a breakfast cereal group. That much flexibility they are ready to allow. Or this is a personal wash category. So here you would get only personal wash. But even then, you have at least 250 different personal care products. 250 of them you have to search. So it's a very complex, extremely difficult problem. Our demo actually is being shown to the customers in TCS retail lab. So we got this project from the TCS retail vertical. So in a limited constrained environment, it was perfect. It's got very good. But in practical scenario, it's very tough problem to solve. Anyway, by the way, there are benchmark data sets available. So if any of you wants to dirty your hands in this problem, you can get these data sets and try solving this. Okay. So what was the initial attempt that we did? We have an ECCD paper on this one. The initial paper was kind of a brute force method. So let's say this is my marketing image available. And remember, the marketing image camera resolution, everything is different than the one image taken here. You have no idea 1 inch here is what is that 1 inch in that. So resolution wise is something different. So we applied a brute force method. We have taken these, put it here, and trying to match correlate all possible ways, right? All possible ways and all different positions. So these are those boxes that we get. Likely boxes here, and then out of these set of boxes, find out the winner, which is the best match. That's a brute force method. It's a very computationally intensive process, but then time is not a problem. Time is not a problem. You can take time, but this is a very simple correlation kind of problem. Correlation between these marketing image and the rack image. So this is how you can look at the problem. You take these Tetli chai image, find out, synthetically make hundreds of versions of it. Every origin, every position, you try to search. Is that the okay? And naturally, you have n times p times s. S is different scaling. N is the number of blocks, and p is the number of heights. So the box may be exactly here. The box may be a little bit up. Well, at different positions, you don't know. You're trying to find them. So many number of correlations. And then therefore at every point you actually get some correlation score of the product. So these are possible products at a particular location you are trying to match, and this is the best score that you get. Right? So this histogram you will get at every point, every column position. Yes? And maybe you will say immediately jump to the conclusion, okay, this is the best match, highest score. So if it is the highest score, then this product is there at this position. Now, if this product is at that position, the width of that product, which you don't know, within that width, no other box can stay. Naturally, the next box will start after that. But you don't know the width, because you have a best guess only. Why you don't know the width? Because marketing image image width and the rack image width, you don't know the relationship between them. So what we are going to get is basically a number of possible solutions at every point. We call them hypotheses. And through our experimentation, we have seen that if you take top 3 hypotheses, you probably going to get the result out of that top. So that's a heuristic. So, but you take the top 3 match and then probe deeper into it. Is that understandable what I mean? So at every point you're doing multiple matches, take the top 3, the top best matches. And then it's a graph theoretic problem. Let me just keep that quickly. So what you can now see is that at every point, this location, these 3 possible products. Next position, 3 product. Next position. So entire rack positions, all column positions. I can have these three nodes. Then I come back to that network flow problem. So I have a source. I'll have a. Let's keep that. So these are the scores, how good those matches are. So I have a source node, all possible paths, and then I'll also have a sink node, all possible paths. Then you will find out the minimum cost flow within the network to find out the organization process. Because I know that if the RAID is the winner here, RAID has a certain width. Within that width, no other box can stay. And as soon as this box ends, the next box comes.
Nodes are bounding box.
Nodes are bounding box. The top three winners of that correlation zone. Okay. Now, this was our initial target. Then we modified this graph theoretic approach in multiple different ways. So one of the constraints was, as you can see, that this is an interesting graph theoretic problem because these widths are not very reliable because it's just a best guess. Why? Because the camera used for that capturing the particular stone is not the same camera, the resolution is different. So these paths can, multiple several paths, multiple layer of this graph can be designed. So you can think of a graph where these are the node structure, and also there are, let's say there is a z-axis coming out of the board, and along the z-axis you also have nodes, which represents the different possible widths, because you have an uncertainty on the width. So anyway, so complex different structures can be possible. We have uses, we have changed the weights of the edges. We have actually find out a confidence score, how confident we are on these nodes. And based on that confidence, we propagated the flow, the cost flows within the game. So this is how we calculated certain confidence value, confidence score. So that means we are saying that we are more certain on the Tetley here, but less certain on the Kellogg's there. So that kind of certainty score is we could calculate. And that score is going to boost the flow of the part. Okay, so that's basically the architecture. I'm not going to the details of this, and essentially finding out the shortest path in the graph is the result. So this is one of the reconstructions of this image, and you can see that some of them are good, some of them are pretty bad, but that is how these reconstructions are. Some of them may be dominated by a particular color. So we tried with different color spaces. Not RGB is not the right space, but what is that right space is very difficult to determine. So that the effect of color, because the blue taken from a particular camera completely changes with another camera. So the blueness, redness, this color value actually changes. And because of the lighting condition, store level illumination is completely different from the market illumination. So that's is yet another challenge in the process. Okay, let me just skip that. We have introduced a node emphasis process by looking at the confidence scores. How about the time? What is the time now? 5 minutes? 5, 10? Okay. I will just skip the details of this. Now, but this gives us important directions of research. If we try to use this graphical modeling in a little bit different way. So, rather than using those correlation score, one other possibility is using a standard classifier like a deep learning architecture, CNN, and the product templates will come, and from the product templates, CNN is going to give me a set of potential regions where those boxes will come. So basically replacing that correlation structure using a deep neural net architecture. So what you're going to get is, this is the complete pipeline. This is the RAG image, exemplar driven. Why we are saying exemplar driven? Because these examples are those marketing images. These exemplar images are available. Classify these region proposals, and then we can introduce some sort of a graphical non-maximal suppression method to find out the winner. If you remember the last problem that I described, we also finding a winner. 3 possible winners. Out of that, who is the best? So here we are calling that as a non-maximal suppression. And can this non-maximal suppression be done using a graph? That is what I will present next. So essentially, these are the 2 areas where we contributed. I'm not going to discuss this part. I will just concentrate straight away in the non-maximal suppression. So there is an attempt to measure the scale, estimate the scale, and then extract the regions. That's the overall scenario. And this is the graph-based non-maximal suppression part that finds out the winner of the possible boxes. These are the marketing images that is getting into the system to recognize the possible locations. So this is one example on a set of products which are hanging on the wall hangings. All these are those boxes, all possible boxes. As you can see from that even if you put a threshold that maybe per product I allow only 100 boxes, out of the 100 you have to find out the winner, the best match. So if you do a straightforward winner calculation, that means our CNN last layer, let's say a softmax layer, gives me the best possible one, right? Threshold. This is the kind of weight that you're going to get. For some cases, the result is excellent. Some cases, it completely misses the region of interest. Right. So this is a brute force non-maximal suppression based on the maximum score of the fully connected softmax layer. So these are some of the other examples for lip care products. Right? So the company is allowing us to say that, okay, only take the lip care products and try to find out the lip care products here. So that allowance is given by the company. Even then, the brute force works, sometimes works good, and not only finding out the best bounding box, it has to also match the correct product. It may happen that it is something Nivea of a particular type, we recognize as a Nivea of something else. And then even if you have correctly identified, you have not correctly identified the product type. So type and the area is very important because they have a plan. So they always match with the plan. And then the problem is for plan from compliance. If it does not match, then the original manufacturer actually pays penalty. Put the penalty on the retail. So there is a complex relationship, financial relationship between the manufacturer and the retailer. So they not only want to know the exact position, they also want to know the type of the. This is on a lab data set. So Chennai, they have a retail lab where they collect it. So we have a huge amount of data on this. These are deodorant products, which is relatively easier to identify. So essentially, the problem boils down to this. We have thousands of such region proposals. All of them are potential winners. Find out the best winner. Suppress the non-maximals and using a graph. And as I was saying that this is a greedy non-maximal suppression, you can see that even if you do a greedy non-maximal suppression, you identify the box correctly, but this goes to a wrong category. Just because one is a 300 gram pack and one is a 500 gram pack. So 500 gram pack you cannot identify a 300 gram pack, or bicycle. Then it's wrong, even though the box is almost right. So we try to look at some of these benchmark and identify exactly the product and this through our graph-based solution. Okay, so the graph-based solution actually looks like this. We'll have series of such possible regions, and you have, let's say, H1 to H6, H1, H2, H5. Some of them are overlapping, some of them are not overlapping, and some of them you can find out that maybe completely wrong, but you cannot ignore it at these stages. So you can have a set defined which you call as an ordered proposal. So these are all proposals, regional proposals, but these are all ordered regional proposals. Each of them has a confidence score, and the confidence score comes from the CNN softmax level. Then let me just skip all the details. We actually modified this confidence score with certain criteria. The criteria, as you can see, so what could be a possible criteria? I mean, if we look at the example here, now if H1 and H5 overlaps, and they are all pointing out to the same product, maybe the possibility of that product has increased. So your confidence will increase if all of them are saying that it's Kellogg's cornflakes 500 grams. That's no doubt about it. All of them are pointing to one product. The problem comes if all of them are giving confusing signals. Right? So therefore, you look at our potential confidence score, that standard deviation is basically measured among the students. If the deviation is very high, then the confidence goes lower. I mean, it's a kind of an intuitive explanation of the process. So we so in one sense, this is coefficient of variation. So we have actually done a modified coefficient of variation of those confidence scores and use that for again a graphical model. We have a source node, sink node. All these are possible regions, and again find out the best path, the best collections of the region proposals that gives me the box. So if you're interested to details of it, just let me know. I can share you on our papers and work. Okay. So these are actually looking at different possible paths, and the path that provides longest path that provides the detected path. So these are some of the analyses. You can see here, if you take a brute force maximum, you probably miss both of them, find out the only this one. Whereas by allowing confidence score to grow, you have a much better result, at least in service. These are some of the examples of these are the proposals, greedy approach. This is our proposal approach. Calculated the standard matrices. These are different comparisons. These are on the benchmark data sets. So these are publicly available. Most of the data sets that I was showing, those are not publicly available. But these are publicly available. I think I'll stop here. What is the time? Boring you too much? Oh, it's almost 50 minutes. I'll just indicate two applications, related applications, and stop there. So this is kind of an extension of the last problem. So the company came back to us and said, well, enough is enough about identifying product, identifying the gaps, the blank spaces. So it's a gap identification problem. And Vikash is brilliant on this. So he actually built up this ground truth. So these are the gap areas. So in fact, their demand was even give us in millimeters square or centimeters square. This is the amount of gap in the RAM. So unutilized space. And combine this with the identification of the product, so that when you are putting the boxes, that is So anyway, so that's the ground truth gap and non-gap region. There are confusions about gap and non-gap. Whatever we are saying, I think. So for example, here it's not exactly a gap. This is a shadow of the product on the other side. It's almost impossible to recognize. No way to recognize. But we have taken that out from the as a ground truth from the training scenario. Anyway, so overall, we have taken the input image, divided into super pixels, which is a very standard, well-known, sleek algorithms are available. You can download the code, run it, get the super pixels, construct a graph of the super pixels, and then you, on the graph, the super pixels, you have a node and edge, get the node feature and edge features, and pass it back to a structured SVM. Why SVM? Because essentially it's a binary classifier. You say black or white, gap or no gap. So therefore SVM is an ideal scenario here, but the features of the SVM are coming from node and edge feature extractor. It's a Siamese network, same kind of network working for two different. Anyway, let me just keep the details because it will take some time. But this is an interesting applications of these are some of our ground truth and predicted results. This is also published in the pattern recognition. This is on human actions. Again, one of the challenges here is the camera is far away. Therefore, you cannot split the limbs separately. Now, there are data sets where it is possible to segment the hand, or head, or leg, or torso. It's not possible here because the camera is far. So, entire thing is one block. So, you have to more concentrate on the position of the block, position and functionality of the block, rather than segmenting it. So, I'll not go over this. So, the point I just wanted to, since I'm presenting on the graphical model, we looked at the block. It's a video. So we actually created a graph, a post graph of actions for the video. So assume someone is jumping. So if someone is jumping, then if you have a jumping video and you divide them into small molecular units, then one of those molecular units will be repeated multiple times. So there is a sequence which is getting repeated. If someone is walking, left leg, right leg, left leg, right leg, so these actions will be repeated for some period of time. And if you put them in a graph, the node which will be kind of multiply connected will be dominant, central, so therefore easy to identify. That understand? So an action is divided into small action units, and we are saying that some action units are getting repeated. If it is repeated, it will be dominant in a graph. If it is not so repeated, then it will be at the periphery of the graph. Now in the graph theory, we have this, for a graph you can have a centrality measure, you have an eccentricity measure. So if a action unit is very central, high centrality value, then that can be used to identify that. All are kind of eccentric, not very peculiar or particular. So this is how we have done post ranking and used this. So extended it for these data sets are also available where not one person action but two persons action, for example, handshaking, kicking, punching. So you can bipartite graph rather than a. Okay. So one of the conclusions is that there are many interesting applications where graphical models can be utilized. I've just shown you some of them with which we worked. Graph convolution-based networks are particularly useful when you have a irregular definition of neighborhood. If it is a very regular neighborhood, then the problem will be a little bit simpler. For example, post graph, some action is getting repeated. Other actions, relationship of other action units with respect to these actions are not in a very regular fashion. In an image, the neighborhood is very regular. 4 neighborhood, 8 neighborhood, or it is a 3D image, it's a 6 neighborhood, 18 neighborhood, definition of neighborhood is regular. But if it is irregular, if it is non-linear, then maybe graphical recognition is a good approach to work. Okay, thank you. And no question.